Okay, drawing resonance structures of a molecule. First thing, there are 3 moves you can make, and only 3. You can move a pi bond to create a new pi bond. You can draw a lone pair to another pi bond, or you can take a pi bond and change it into a lone pair. Those are your only 3 options. Now, things to think and keep in mind is look first of all in your molecule for C+ or C-. Resonance will occur around those atoms, if at all possible. Those are very good places to start. Again, this first molecule here, we have a plus. Resonance, think of it as moving electrons in the pi system. Electrons are really attracted to positive charge. And so what we can do is take these electrons in the pi system and swing them over here. We use a curved arrow to show electron movement. So we're moving these 2 electrons, swinging them over to there. And when we do so, we create a resonance structure. Now, this structure here has a net positive charge. That means this structure down below must also need a positive net charge. Notice we're moving electrons, if we have A, B, and C, we're moving electrons away from atom C. They're still attached to atom B. So if we're moving electrons away from atom C, that is where they end up going. Moving 1 electron over to there, like so. Now, this structure right here, we start out with a negative charge. Electrons flee negative charge. So think of it, we start out with this lone pair. These electrons form a new pi bond here. That kicks these electrons from this pi bond up onto the carbon. So we get double bond like that. Negative charge right there. Now, just because you have a positive charge or a negative carbon does not mean you'll have resonance. For example, we have this molecule. We have a carbocation here. We have a pi bond. We can't move this pi bond to this carbocation because you need to have the pi bond connected to the carbon attached to your carbocation. Another way of putting it is you need to have p orbitals all the way through. This carbon, this atom right here, is sp3 hybridized. sp3 means no p orbitals. This kills resonance. So this molecule has no resonance structures. But you cannot move electrons past an sp3 hybridized atom. Let's take a look at this molecule. I have nitrogen with a lone pair. Sometimes molecules don't have, actually quite often, they're not going to have a carbocation or a carbanion. So next you need to look for nitrogens and oxygens, because there are also sites where there will be resonance. Here we have a nitrogen with a lone pair. Attached to this nitrogen with a lone pair is an sp3 carbon, an sp3 carbon. So we're not going to use this lone pair to go to either of those 2 carbons because neither one has a p orbital. On the other hand, we have an sp2 carbon up here. So to draw a resonance structure, we can start with its lone pair, and we can send it down to that sp2 carbon, forming a new pi bond between this nitrogen and this carbon, which has a p orbital. That forces these electrons to there. This gives us this. Take a look at this. We have an oxygen, double bonded oxygen. Notice there are no formal charges on this molecule right here. That means this oxygen, in order to be neutral with no formal charges, it has to have 2 bonds and 2 lone pairs. Notice the pi bond is directly to the oxygen. Here, the pi bond isn't directly to the nitrogen, it's adjacent to the nitrogen. Here it's directly to the oxygen. When the pi bond is directly to an oxygen or a nitrogen, we move the electrons from the pi bond to sit on top of the oxygen. This is the move. Pi bond becomes a lone pair. Now we have negative charge there, positive charge here. Okay. These last 2 examples, this molecule can be represented by, the nitrogen molecule can be represented by this structure or this structure. The 2 structures are not equivalent. There's one that better represents it. The more stable one better represents the molecule and should be drawn. The more stable one is referred to as the major structure. And when it comes time to determine which structure is major, you have 3 rules to follow. The first and most important rule is the octet rule. If a molecule has all the atoms in there with a complete octet and another one doesn't, the molecule with a complete octet automatically major. But if all the molecules have a complete octet, then we have to go to rule 2. It's very important to follow these in order. That's minimization of formal charge. In this case, this nitrogen, complete octet. All these carbons, complete octet. Same way here. Everything has a complete octet. But in this first case, we have no formal charge. This bottom case, we have 2 formal charges. By rule 2, this structure up above is major. Let's take a look at the carbonyl, the ketone. Here we have a neutral oxygen, neutral carbon. All the atoms here have a complete octet. This structure here, we have a C+. A C+ has 6 electrons. By definition, it does not have a complete octet. So anytime you have a carbocation, that's probably not going to be your major structure. Here, complete octet, this is the major structure. Let's take a look at this molecule right here. What we can do is draw resonance structure. Again, we have a pi bond to a nitrogen. So we can move that onto that nitrogen. Double bond nitrogen. So we get a negative charge on this nitrogen, a positive charge on this carbon. Like that. Molecules aren't limited to one resonance structure. There can be multiple resonance structures. Notice once we have generated this C+, we are next to a pi bond, we can move these electrons over again. And so this molecule has 3 resonance structures. The major resonance structure is the blue one, again because of the octet rule. This molecule right here, we have a carbocation flanked on 2 sides by sp3 carbons. Because this has a double bond here, but you have the sp3 carbon here, that double bond cannot move to this carbocation. It's basically isolated. But we do have an oxygen present here. Because you have an oxygen present, and oxygen can donate its electrons, like so, to form a pi bond. Positive, there, like so. Now, which one of these is major? Well, this first one, let's go through the octet rule. This first one has a C+. This violates the octet. This one down below does not have a C+. All its atom has a complete octet. This is the major structure. It does not matter that you have a positive oxygen versus a positive carbon. That does not come into play. The important part is the octet rule. The octet rule is satisfied. That makes this the major structure. And the third rule, does charge make sense? This rule is the most misleading rule. This is a last circumstance only type rule. Only when you cannot decide between using rule 1 and rule 2 do you go to rule 3. Only then. This molecule here, C-, and we have an oxygen. Since we have a C-, let's start there. C- goes here, forms a new pi bond, and that kicks these electrons up onto this oxygen here. And you do so. Get negative charge on this oxygen. Double bond here. Let's check. This molecule has a complete octet. This molecule also has a complete octet. Rule 2, minimization of formal charge. This has a single negative charge. This has a single negative charge. Tie. Only now, when we have looked both at 1 and 2, can we go to this charge makes sense. Negative carbon versus negative oxygen. Negative oxygen wins out. This structure here is the major structure. Okay. Now, with this last resonance structure, it might have been tempting to draw a resonance structure like this because of double bond oxygen. Double bond goes up to that. And get this structure. Which hopefully you can draw better on your notes. What makes this one bad? Not just the sloppy drawing, but this is a case where you have a C+ and a C- on the same molecule. Do not draw that. Those make very bad resonance structures.